Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So take a look at a glass of water, just picture it sitting there right on your kitchen counter. If you were to take that glass, isolate just a single drop of it, and ask the absolute smartest planetary physicists on Earth to analyze its atomic signature, well, for the last 40 years or so, they would have told you a very specific, a very dramatic story about where it came from.
Yeah, a highly dramatic one.
Right. They would have told you that the water you're about to drink was delivered by this massive bombardment of icy comets and frozen asteroids from billions of miles away, from the absolute darkest, coldest edges of the outer solar system.
It was basically the ultimate cosmic import business.
Right.
I mean, the prevailing scientific consensus was just absolutely locked in on this idea that the Earth was born dry.
Completely dry.
Yeah, completely. And that it required this massive chaotic delivery system to become the blue marble that you know today.
Right. But today we know they were wrong, completely wrong.
Yeah.
The water in your glass, the ground beneath your feet, the mountains, the oceans, literally the entire mass of the Earth, it wasn't imported at all.
No, not even a little bit.
It was locally sourced.
Mm-hmm.
And we are going to explore exactly how researchers at ETH Zurich, specifically planetary scientists Paolo Sosi and Dan Bauer, have completely rewritten the recipe for our planet. I mean, they've proven that the Earth is a 100% local creation.
Which is just a massive fundamental paradigm shift. We're talking about dismantling decades of accepted planetary science here.
Decades of it, yeah.
Because when you prove that the Earth didn't need the outer solar system to get its water, you aren't just changing the history of one planet. You're completely altering our entire understanding of how star systems form.
Wow.
Yeah, and how volatile elements survive, and ultimately, what the actual recipe for a habitable world really looks like.
Okay, let's unpack this, because to really grasp the magnitude of what Sosi and Bauer have uncovered, we need to first thoroughly understand the old consensus. Why was the scientific community so utterly convinced that we needed this elaborate cosmic delivery service in the first place? Why did they think that, I think it was up to 40% of the Earth's mass had to come from beyond Jupiter?
Well, it really all comes down to a concept called the snow line, or sometimes it's called the frost line, in the early solar system.
Okay.
So when you look back 4.5 billion years, before the planets were actual spheres, the solar system was just this flat protoplanetary disk.
Basically just a swirling cloud of gas and dust.
Right.
Orbiting the really young, highly energetic sun.
Exactly. And the physics of that disk dictate a very severe temperature gradient. Close to the sun, where the Earth was busy forming, the ambient temperature of this swirling gas and dust was just incredibly high.
Like an oven.
Yeah, a scorching environment. And in that kind of heat, volatile elements, which are elements and compounds with really low boiling points, so primarily water, but also things like carbon and nitrogen,
right,
they simply cannot condense into a solid form. They just remain as a vapor. And the intense solar wind of the young sun just relentlessly pushes that vapor outward.
So the inner solar system is essentially this giant cosmic oven. I mean, it's like baking a highly specific cake. You can't bake water into a rock if the ambient temperature is hot enough to instantly vaporize it, right?
Precisely. To find any solid ice, you had to travel far, far out into the disk, well beyond the orbit of where Jupiter is today.
Way out there.
Yeah, because out there, past the snow line, the temperatures finally drop low enough for water vapor to actually freeze onto the tiny dust grains, which then create icy pebbles, and eventually you get these massive icy asteroids and comets.
Which naturally leads to the old assumption, if the Earth formed inside the oven, it must have been baked bone dry.
Right. That was the logic.
But clearly, we have oceans, so the old logic dictates that once the oven cooled down a bit, someone or something must have thrown a huge bunch of ice into it. But if the inner solar system was considered this hot, dry zone, wasn't the assumption of an outer system water delivery just entirely logical based on the physics?
Oh, absolutely. It made perfect sense based on the older models. In fact, things like the Grand Tack and other planetary migration models were heavily relied upon to explain this exact mechanism.
A Grand Tack.
Yeah, so scientists hypothesize that the giant planets, particularly Jupiter and Saturn, they actually migrated inward and then outward during their early formation.
Oh, wow. They moved around.
Yeah, a lot. And this gravitational dance would have totally destabilized the orbits of countless icy, water-rich bodies in the outer solar system. It would have sent them hurtling inward to crash right into the early dry Earth.
So it was just this violently chaotic mechanism designed specifically to solve the water problem.
Exactly. It made perfect logical sense based on the thermodynamic models of the time. But what's fascinating here is that Sosi and Bauer's new calculations completely dismantle that entire logic.
Completely.
Yeah. Their analysis reveals that material from the outer solar system accounts for less than 2% of Earth's mass. And honestly, their data suggests it's potentially 0%.
Zero. I mean, the imported ingredients simply aren't there at all. The Earth was built entirely from the dry, supposedly volatile stripped materials of the inner solar system.
Yes.
Which is just absolutely staggering to think about. But it begs a really massive question. If we are completely overhauling a 40-year-old consensus, I mean, the proof has to be ironclad.
Oh, it has to be undeniable.
Right, because we weren't there 4.5 billion years ago to watch the Earth accrete. So how do we definitively prove where a rock actually formed?
Well, we look at the atomic fingerprints locked inside the rocks themselves. Specifically, we look at something called nucleosynthetic isotopic anomalies.
Okay, let's dive deep into that, because this is really the core of the whole discovery. When we talk about isotopes, we aren't just talking about slight variations in weight, are we? We are actually talking about the distinct chemical memory of dying stars.
That is the perfect way to phrase it, honestly. Before our sun even ignited, the giant cloud of gas and dust that would eventually become our solar system was seeded with material from various stellar phenomena.
Like what kind of phenomena?
Well, some dust came from the gentle, slow shedding of red giant stars, and other dust came from violently explosive supernovae.
And each of those different stellar events produces different flavors, basically. Or isotopes of the elements we know, right? Like titanium or chromium.
Exactly. And crucially, this pre-solar cloud was not perfectly mixed. It wasn't uniform.
Okay.
It was like a really poorly stirred cake batter. There were pockets with a slightly higher concentration of supernova dust, and then other pockets with slightly more red giant dust.
Oh, right.
And as the protoplanetary disk formed and started spinning around the young sun, these subtle variations in the isotopic ratios, these anomalies we're talking about, they were permanently preserved in the specific regions where they coalesced.
So if a rock forms in the inner solar system, it permanently locks in the specific isotopic batter of that local neighborhood.
Yes.
And if it forms out past Jupiter, it locks in a completely different isotopic signature. So it's basically a permanent built-in barcode.
It is a literal barcode. But, reading that barcode has historically been incredibly difficult for scientists. For decades, the entire field of cosmochemistry relied almost exclusively on the isotopes of a single element to try and trace these origins.
Which was oxygen, right?
Yes, oxygen.
Why just oxygen? Is it just because it's everywhere?
Largely, yeah. Oxygen is incredibly abundant in rocky materials. I mean, it makes up a huge percentage of silicate minerals. So it was simply the easiest thing to measure in the lab.
Sure.
But relying on oxygen comes with a severe limitation. Oxygen is a highly volatile element. And in the early solar system, a vast, vast amount of it was just floating around as a gas, like carbon monoxide or water vapor.
Ah, so it interacts with stuff. It mixes.
It interacts constantly.
Yeah.
The oxygen in a solid grain of dust can very easily exchange its isotopes with the oxygen in the surrounding gas. It's totally fluid.
Oh, wow.
Therefore, the oxygen isotopic signature of a rock can be altered, blurred, or just completely overwritten by its environment long, long after it initially formed.
So it's not a reliable barcode at all.
No. Using oxygen to trace a rock's origin is kind of like trying to trace the origin of a specific drop of water in a flowing river. It's just too easily compromised.
Which brings us to the real breakthrough in the early 2010s. Researchers realized they needed to look at elements that don't interact, right? Elements that just refuse to change their signature no matter what. And they landed on things like titanium and chromium.
Yes.
Why those specific elements?
Because titanium and chromium are what we call highly refractory elements.
Meaning they like it hot.
Extremely hot. They condense from a gas into a solid at incredibly high temperatures. We're talking well over 1,000 degrees Kelvin.
Wow.
This means they were among the very first elements to actually solidify out of the hot solar nebula. And here's the key. Once they lock into a solid mineral structure, they absolutely do not exchange isotopes with the surrounding gas.
They are stubborn.
Very stubborn. They perfectly preserve the exact nucleosynthetic signature of the local dust from the earliest possible moments of the solar system's formation.
So they are the perfect witnesses. They saw the solar system form, and they locked their memory in a vault. And once planetary scientists started using these refractory elements, it completely changed the map of the solar system, didn't it? It allowed them to split all meteorites into two very distinct, unarguable categories.
It did. You had the non-carbonaceous meteorites, which formed exclusively in the inner solar system, and then the carbonaceous meteorites, which formed way out in the outer solar system, past the orbit of Jupiter, and contained significantly higher amounts of water and carbon.
Okay, here's where it gets really interesting. Because if we've had this incredibly precise titanium and chromium fingerprinting method since the early 2010s, and we've had meteorite samples from the asteroid Vesta and from Mars for decades, right?
Right, have.
Then why are we only finding out right now that the Earth is entirely non-carbonaceous? Why didn't someone figure this out 10 years ago? Was the old oxygen-only method just too blurry, or was there more to it?
Well, if we connect this to the bigger picture, analyzing just titanium and chromium is still only giving you a two-dimensional view of a vastly complex system. If you want to definitively prove that Earth contains absolutely 0% outer solar system material, you really cannot rely on just two data points.
Even if they are highly reliable data points.
Exactly. Think of it like a forensic investigation. If you find DNA at a crime scene, checking just two genetic markers might tell you the suspect is from a certain hemisphere, right?
Right.
But it won't give you their exact identity.
Right, the error bars are just too wide.
Yes. If the isotopic data for Earth, Mars, and the carbonaceous meteorites are plotted on a simple two-dimensional graph using just titanium and chromium, the data points have these tiny margins of error that can sometimes overlap.
Oh, I see.
And that overlap leaves room for doubt. It leaves room for a scientist holding onto the old theory to say, well, maybe there's a 5% mix of carbonaceous material in there.
So the little cosmic import model still had room to breathe inside those tiny margins of error.
Precisely. To truly eliminate the margins of error, you have to drastically increase the dimensionality of your data. And that is exactly what Paolo Sossi and Dan Bauer did. They didn't go out and discover some brand new shiny rock. They orchestrated a total triumph of methodology.
Yeah.
They gathered existing isotopic data on 10 different element systems.
10. So we're moving from a simple two-dimensional graph to a 10-dimensional mathematical space.
Exactly. They looked at the isotopes of iron, calcium, molybdenum, ruthenium, tungsten, neodymium, and several others.
Wow.
And each of these elements condenses at completely different temperatures and has slightly different nucleosynthetic origins.
But human brains can't even visualize a 10-dimensional graph. I mean, how do you even begin to map the isotopic signature of Earth against meteorites in 10 dimensions?
Well, you have to step out of the realm of traditional geochemistry and enter the realm of advanced data science. The researchers utilized specialized statistical calculations, specifically dimensionality reduction techniques. Think of methods akin to principal component analysis, or PCA.
Okay, break that down for us, because this sounds like taking a dusty library of old, handwritten census records that historians have stared at for decades, applying a modern statistical algorithm to them, and suddenly uncovering a completely hidden family tree that rewrites history. How does a tool like PCA actually work on chemical data?
That's a great analogy. So imagine you have this massive chaotic cloud of data points representing all these different meteorites, and they are floating around in a 10-dimensional room. To the naked eye, it just looks like random noise.
Just a mess of dots.
Right. But PCA is a mathematical algorithm that essentially rotates that room. It looks for the specific angles where the data naturally lines up. It finds the underlying structure, the hidden axes of variance that explain the most significant differences between all the samples.
It's almost like taking a really complex three-dimensional sculpture and rotating it under a single light until it casts a perfectly clear, recognizable two-dimensional shadow on the wall. You are just finding the specific mathematical perspective that reveals the truth hidden in all that complexity.
That is a phenomenal way to picture it. And when Sossi and Bauer applied these statistical models to the 10-isotope dataset, the shadow it cast was undeniable.
Yeah.
In this high-dimensional space, all the non-carbonaceous meteorites, so the inner solar system rocks, they formed a perfectly straight, super tight line.
Okay.
Mars is right on that line. The asteroid Vesta is exactly on that line. And the Earth sits squarely on that exact same line.
And where are the carbonaceous meteorites, like the icy water-bearing rocks from the outer solar system?
They are completely segregated. They form their own separate, distinct cluster in a totally different area of the data space. There is zero overlap. No margin of error whatsoever.
Which brings up a really critical point about how science is often conducted. For decades, researchers were looking at these exact same rocks, but they were looking at them through the lens of a preconceived physical assumption, weren't they?
Absolutely.
They assumed the Earth needed outer solar system water, so when they built their models, they inherently biased the math to allow for a mixture.
Yes. We call those Bayesian priors. When you construct a model to test a hypothesis, you often feed it prior assumptions based on what you already think you know.
Right.
The older models basically instructed the algorithm, hey, find the best mixture of inner and outer material to create the Earth. And the algorithm, just doing what it was told, found a mathematical way to mix them, even if physically it was highly improbable.
It's the old adage, right? If you torture the data long enough, it will eventually confess to anything.
Exactly. And the real brilliance of Bauer's contribution here is that their model is entirely agnostic. They completely stripped away all those thermodynamic assumptions about hot inner disks and migrating comets.
They just let the data talk.
They just let the cold, hard numbers of 10 different isotopic systems speak for themselves. And the numbers do not lie. The calculations are entirely robust because they rely solely on the data itself. The Earth is a closed system. It is 100% non-carbonaceous.
Okay, so what does this all mean? Because this is where the physical reality of the solar system starts to really break my brain. Because if the data undeniably proves that outer and inner solar system materials never mixed, if the carbonaceous rocks and the non-carbonaceous rocks never mingled for millions of years while the planets were forming, we have to ask a massive physical question. What was physically keeping them apart? I mean, the protoplanetary disk is a swirling, violent hurricane of gas and dust. Things should be crashing into each other constantly.
They should, which means there had to be a massive physical barrier.
Yeah.
A dam. And that dam is the biggest, heaviest bully in the planetary playground, Jupiter.
Jupiter. But I want to push back on this a little because the mechanics of how Jupiter acts as a barrier seem entirely counterintuitive to me. Jupiter is massive. It has immense gravity. Wouldn't a giant gravitational vacuum cleaner actually pull more icy comets and rocks from the outer solar system inward? How does a massive planet create a wall?
That is exactly the right question to ask, because it highlights the difference between static gravity and the fluid dynamics of a protoplanetary disk. You are thinking of Jupiter as just a heavyweight sitting in empty space, but you have to remember the environment it was in. Jupiter is forming inside a massive, rotating disk of thick, viscous gas.
Okay, so it's more like a giant rock moving rapidly through a thick fluid.
Precisely. As Jupiter grew, and it grew incredibly fast, accreting huge amounts of hydrogen and helium, its immense gravity began to actually interact with the surrounding gas. It creates what are known as Lindblad resonance.
Lindblad resonance.
Yeah. As Jupiter orbits, it generates these massive spiral density waves in the gas. It's actually very much like how a boat creates a wake as it moves through water.
Oh, I see. So it's actively pushing the fluid away from its orbit.
Yes. The gravitational torque from Jupiter literally clears a physical gap in the protoplanetary disk. It sweeps its entire orbit clean of gas and dust. But it does more than just make an empty lane. By pushing the gas away so violently, it creates a massive pressure bump just outside its orbit.
A pressure bump, like water piling up against a physical dam.
Exactly like that. Now consider the dust in the icy pebbles, the carbonaceous meteorites that are forming out beyond Jupiter. In a normal disk without a giant planet, these pebbles experience gas drag. They feel friction against the gas, they lose angular momentum, and they naturally spiral inward toward the sun.
Right.
This inward drift is a fundamental mechanism of how planets form.
So they are actively trying to drift inward toward where the Earth is forming.
Right. But when they hit that high-pressure ridge, created by Jupiter's wake, the physics suddenly change. The gas in that pressure bump is actually orbiting slightly faster than the normal Keplerian speed. This means the gas drag suddenly acts as a tailwind, rather than a headwind for the pebbles.
Wait, really?
Yes, the inward drift stops completely. The pebbles become physically trapped in this high-pressure zone outside Jupiter's orbit. They can't move inward anymore.
That is just brilliant. Did Jupiter effectively act as a cosmic bouncer standing at the velvet rope of the asteroid belt, physically blocking all those carbonaceous, water-rich meteorites from entering the inner VIP section?
That is exactly what happened. It's not that Jupiter's physically blocking every single rock with its body.
Oh.
It's that Jupiter fundamentally altered the fluid dynamics of the entire solar system. It created a hydrodynamic dam that the icy rocks physically could not cross.
Wow.
and scientists knew Jupiter carved a gap. That wasn't a secret. But until this specific multidimensional isotopic analysis by Saucy and Bauer, the actual permeability of that barrier remained a mystery.
Right, like, did some icy comets manage to slip past the velvet rope?
Exactly. We didn't know if a significant amount of material managed to leak through the dam over millions of years. But this new analysis proves the dam held almost perfectly. The barrier was incredibly tight. Almost no material from beyond Jupiter flowed inward toward Earth. The two zones were strictly segregated.
Jupiter was the great divider, which is an incredible piece of planetary mechanics, but it immediately brings up a monumental, inescapable paradox. The dam held. The icy comets from the outer solar system were trapped behind Jupiter. They never reached Earth. Yet, I can go to my kitchen right now and turn on the tap and water comes out.
Yep.
If Earth only ever accumulated local, dry, non-carbonaceous rocks, where on Earth did the oceans actually come from?
You have hit the exact center of the new mystery. This raises an important question, because by solving the isotopic origin of the Earth, Saucy and Bauer have completely broken our previous understanding of early planetary thermodynamics.
Because if the Earth is completely local, then the water absolutely had to be local too, right? It must have been present in the inner solar system from the very beginning.
Exactly. The researchers concluded that Earth grew within a relatively static system. It simply sat in its inner neighborhood, incorporating the smaller neighboring planetesimals and dust that shared its exact non-carbonaceous isotopic signature.
Just eating local rocks.
Just feeding on its own local environment. And therefore, the volatile elements, the water, the carbon, the nitrogen that literally make life possible, must have somehow survived the inner solar system's oven.
But wait, this completely shatters the timeline. If the inner solar system was so incredibly hot during the protoplanetary disk phase, how could volatile elements like water just sit there without boiling away into deep space? You said earlier that the solar wind and the heat would vaporize volatiles and push them outward. This feels like a direct contradiction of basic physics.
It is a contradiction of the models we built.
Yeah.
Which simply means our models are missing a crucial mechanism. And this is exactly the frontier that Paolo Saucy's team is aggressively investigating right now. The isotopic data is undeniable. The water was local. We have the wet. But the how is now the most exciting open question in planetary science today.
What are the current theories? Because if it's not arriving via icy comets, it has to be hiding somewhere in the dust, right?
There are several really fascinating hypotheses emerging. One leading idea involves the actual chemical structure of the dust grains themselves. We aren't necessarily talking about chunks of free ice sitting around. We're talking about water molecules locked deep inside the crystalline lattice of early minerals, things like olivine and pyroxene.
Oh, I see. So the water is chemically bound to the rock itself, totally protected from the heat.
Exactly. Even at super high temperatures, certain mineral structures can trap hydrogen and oxygen atoms within their matrix. And when these dust grains accrete and smash together to form a planet, the immense pressure and heat of the forming world essentially bakes the water out of the rocks from the inside out.
Wow.
It outgasses it to form an early atmosphere and eventually the oceans.
That implies the rocks of the inner solar system were always inherently wet on a molecular level. That is wild.
It is. Another really compelling theory involves the young sun itself. The early solar wind was fiercely blowing out hydrogen protons. It's entirely possible that these high-energy protons slammed into the oxygen-rich silicate dust in the inner disk, literally creating water molecules on the surface of the dust grains in real time.
Wait, the sun was actively manufacturing water on the surface of local rocks?
Yes. It's a localized, highly energetic chemical reaction. And, another factor might simply be that our temperature models of the protoplanetary disk were just too simple.
In what way?
Well, the disk wasn't perfectly transparent. It was thick and murky with dust. It's highly possible that the inner regions experienced significant shadowing.
Shadowing, like clouds blocking the sun on a hot day.
Exactly like that. If dense, thick rings of material near the sun completely block the intense radiation, localized cool zones might have existed much, much closer to the sun than we previously thought. And that would allow water vapor to locally condense or at least survive without being entirely stripped away.
It's just staggering to think about. We assumed for so long that water was this fragile, exotic thing that had to be carefully delivered to a dry world. But the reality might be that water is just incredibly resilient, it's stubborn, it finds a way to bake itself into the very foundational dust of a planetary system, even in the absolute hottest, most violent environments.
Which is a perfect segue into the much broader implications of this research, because the implications of this static local growth model do not stop at Earth's atmosphere.
Right.
If this multi-dimensional isotopic analysis works perfectly for Earth, Mars, and Vesta, can we use it to unlock the secrets of the planets we literally cannot touch?
You're talking about Mercury and Venus, right? The two innermost planets.
Yes. So Saussure-Bauer's mathematical model predicts that Venus and Mercury lie on the exact same non-carbonaceous isotopic line as Earth and Mars.
Meaning they're also 100% locally sourced. They share our exact cosmic barcode.
The model strongly suggests a uniform, static building process across the entire inner solar system. It implies that heliocentric distance, basically how close you are to the sun within that inner region, does not fundamentally alter your primary isotopic building blocks.
But there is a massive catch here regarding the scientific method, right? Because while Saussure can predict their makeup mathematically all day long, he cannot verify it analytically right now.
Right. It's the ultimate frustration of theoretical prediction. The math strongly dictates that Venus and Mercury are made of the exact same isotopic stock as Earth. But to prove it beyond a shadow of a doubt, they desperately need physical evidence. And humanity currently possesses absolutely zero physical rock samples from Venus or Mercury.
We've never landed a sample return mission there, and we haven't found any meteorites that we can definitively say were blasted off the surface of Venus and landed here on Earth.
No, we haven't. We have Martian meteorites, we have pieces of Vesta, we obviously have Earth. But Venus and Mercury are just locked away in the deepest part of the solar gravity well. So the prediction stands as a monumental test.
Just waiting.
Yeah, waiting for future space missions, like the upcoming Da Vinci or Veritas missions to Venus, to eventually provide the chemical data that will either confirm or deny this math.
But even without holding a single physical rock from Venus, it fills you with sheer awe. Just think about the power of this capability. Data science, applied to geochemistry, essentially allows us to peer beneath the crushing atmosphere of Venus. It allows us to mathematically deduce the origins of a planet we literally cannot touch.
It really is incredible.
And if we can do that for Venus, what happens when we turn this mathematical model outward beyond our own solar system?
Well, that is precisely where the team is focusing their next frontier, applying these processes to exoplanetary systems.
This is where the local growth model really changes everything, because if the Earth got its water locally, what does that mean for planets orbiting other stars?
Historically, when astrobiologists calculated the odds of finding a habitable, ocean-bearing world around another star, the math was incredibly depressing. Because if you absolutely require the cosmic import model, you need a highly specific, rare sequence of events.
Oh, right. You'd need a rocky planet forming in the habitable zone, A and D. You'd need an outer asteroid belt completely full of ice. A and D, you'd need a massive gas giant like Jupiter to migrate at exactly the right time to throw that ice inward. All without accidentally throwing the rocky planet right into the sun.
Exactly. It makes the recipe for a habitable planet look like a freak accident. A cosmic lottery ticket that requires immense, almost impossible luck. But if Saussure-Bauer's model holds true, if a planetary neighborhood is naturally static and water is inherently baked into the local dust from the very beginning, surviving the intense heat of the inner disk,
then the gas giant isn't a delivery service at all. It's just a dam. And you don't even necessarily need it to deliver anything.
Right. It implies that the formation of water-rich rocky planets is not this complex multi-stage billiard game. It might actually be the standard universal default way that terrestrial planets form. The volatile elements are already there in the disk. When a rocky planet accretes, it simply scoops them up.
Imagine how this accelerates our search for Earth-like exoplanets. I mean, it means that almost any rocky planet forming in the habitable zone of its star could naturally possess the ingredients for oceans and an atmosphere right from this inception. It drastically increases the statistical odds that the galaxy is just teeming with blue worlds.
Conceptually, it completely rewrites the Drake equation variables for planetary habitability.
Yeah.
But as with any massive paradigm shift, we do have to reinforce the reality of the scientific process here.
Yeah.
It's not going to be accepted overnight.
I can imagine.
Yeah. So Odysseus himself admits that despite these incredibly robust multidimensional findings, he and Bauer are bracing for what he calls many heated debates.
Oh, I bet. You don't just upend a 40-year-old consensus about something as fundamental as where the oceans came from without ruffling a lot of academic feathers. There are probably entire careers built on those older planetary migration models.
And overturning them requires immense scrutiny. The scientific discourse over Earth's building blocks is far from over. Other planetary scientists are going to rigorously attack their statistical methods. They will try their hardest to find flaws in the principal component analysis. They will relentlessly demand explanations for the thermodynamic paradox of water surviving in the inner system.
They will demand to know the how before they fully accept the what.
Exactly. And that is exactly how it should be. The fierce pushback is a healthy, absolutely necessary part of the scientific method. It forces the researchers to dig deeper, to find the exact chemical mechanism of water preservation, and to make their models even more bulletproof.
It's the crucible of science. You put the idea in the fire, and if it survives, it becomes the new truth. And right now, the local growth model is looking incredibly resilient.
It is entirely transforming how we view the ground we walk on every single day.
It really is. So let's briefly recap the incredible journey we've just been on, because it is a mind-bending shift in our relationship with the planet.
It really is.
For your entire life, you might have assumed, like the most brilliant scientists in the world did for decades, that you live on a planet built from exotic, far-flung cosmic imports. You might have looked at a glass of water and thought you were drinking melted comets delivered from the freezing, dark edges of the solar system in this violent game of celestial pinball.
But the atomic barcode, written in the refractory elements of titanium and chromium and analyzed through the revolutionary high-dimensional lens of modern data science, tells a completely different, profoundly elegant story.
You actually reside on a completely locally sourced world, a planet built entirely from the dry, dusty rocks in its own immediate neighborhood. A world that was protected from outside interference by the massive hydrodynamic dam of Jupiter's gravity, and a world that somehow, against all our previous thermodynamic logic, managed to hold on to its life-giving water from the very first moments of its fiery birth.
It completely replaces a chaotic system of chance with a beautiful inherent resilience.
It really does. It takes that complex, imported cosmic supply chain idea and replaces it with something deeply fundamental. So, we want to leave you with a final, lingering question to ponder long after our conversation today comes to an end. Think about this. If Earth's oceans weren't the result of a lucky random delivery system, if the water wasn't a freak accident of a migrating gas giant, but was instead baked directly into the interplanetary dust from the very start, what does that mean for the billions of other star systems swirling out there in the dark? Does it mean the delicate, complex recipe for life isn't a rare, fragile coincidence, but rather a standard, inevitable feature of how the universe builds planets?